Hello, this is the section 4.8 lesson. In this section we're going to introduce confidence intervals for differences. In section 4.5 and 4.6 we introduced confidence interval estimates of a single population proportion and a single population mean. What we're going to be doing here in this section is very similar to what we've done before, except that instead of dealing with a single population, we're going to be dealing with two different populations, and we're trying to estimate the difference between those two population means or those two population proportions. The basic idea in this section is very similar to what we've done before. We're going to start off by collecting sample data, and then we'll select an appropriate critical value, and then calculate a margin of error, and then calculate a confidence interval, which is going to be a range of possible values for what it is we're trying to estimate. The biggest difference is that in this section we're going to be estimating the difference between two population means or proportions as opposed to just the value of a single population mean or proportion. In this short lesson we're going to focus on really understanding the basic idea of what we're doing and the basics of the calculations. We won't get into the theory at all. So our first example is going to illustrate the need to estimate a single the difference between two population proportions. So consider a scenario of a statistics professor who is trying to compare two online homework systems. And so she lets 95 students use the first system, and out of those 95 students, 87 pass the class. And so that means we have about 91.6% of the students in this sample pass the class. Then she lets 82 students use the second system. 62 of them pass the class, and so that means about 75% of students who use the second system pass the class. And so based off of this result, it looks like System 1 does a little bit better than System 2 in terms of the percentage of students who pass the class. But we want to ask the question, is just how much better is the first system than the second system? The first appears to be better, but just how much better is it? Okay. And so let's make a couple of observations here. First of all, we are comparing two independent populations. We're really interested in all students using the first system and all students using the second system. Not just the few students in our two samples who use those systems. We're interested in all students. So we have two populations that we're interested in. And they're independent in the sense that what happens to one population has no effect on what happens to another population. Okay. Now, within those two populations, we're interested in two population proportions. So let P1 be the proportion of all students using the first system who pass, and then P2 be the proportion of all students using the second system who pass. Now, in these two definitions, we stress the word all because we're interested in all students who use the first system and all students who use the second system, and not just the few students in our two samples. Okay. Specifically, what we want to do here is estimate the difference between these two population proportions, P1 minus P2. If this difference is positive, then it would indicate that this first system is indeed better than the second system. If this difference were negative, then it would indicate the opposite. So we're going to estimate this difference with what we call a two-proportion z-interval. Called a two-proportion because we are comparing two different population proportions. Called a z-interval because our test statistic is going to be a z-value. And so first of all, let's let N1 and N2 be our two sample sizes that come from our two independent populations, and then P hat 1 and P hat 2 be the corresponding sample proportions. Our margin of error is given by this rather simple formula, P hat times z sub alpha divided by 2. So alpha is our significance level, which we'll typically take to be 0.05. and then p hat is given by this rather nasty looking formula right here. Okay. So then once we calculate the margin of error, we calculate our confidence interval estimate of P1 minus P2 using this formula right here. So we start off by calculating the difference between our two sample proportions. This number right here is a point estimate of our difference of P1 minus P2. So we take our point estimate, subtract the margin of error, and we take our point estimate and add the margin of error, and we're all done. So requirements for calculating this type of interval are: first, both samples are random and independent. Now requirement of randomness is always necessary. And independent here again means that what happens to one sample has no effect on any other on the other sample. Our second requirement is that both samples contain at least 5 successes and 5 failures each. This is necessary so that our underlying population proportions, underlying random variables representing the sample proportions are normally distributed, at least approximately. And so going back to our example, we were given here that p hat 1 was 0.916 and p hat 2 was 0.756. N1 is 95, N2 is 82. And so now we're ready to start plugging stuff in. First we calculate p hat, and here's our p hat 1, p hat 2, N1, N2, do the arithmetic, and there's p hat. Next, for our margin of error, we'll choose our critical value. No confidence level was given in this problem, so we'll use a 95% confidence level. And so our critical value is z sub 0.05 divided by 2, which is 1.96. And then to calculate our margin of error, we'll take p hat times the critical value, and we get 0.104. And so then we plug those into the formula for the confidence interval. Here's P1 hat minus P2 hat minus E. Do the same thing over here, except we add E, and we get our upper and lower confidence interval limits. Now we would interpret this confidence interval in the same basic way as we interpreted confidence intervals in previous sections. We would say that we are 95% confident that the difference between the two population proportions is somewhere between 0.056 and 0.264. Now the 95% confidence level here means the same thing as it did in previous sections. It means that if we were to construct a whole bunch of different confidence intervals using data from a whole bunch of different samples, then about 95% of those confidence intervals would contain the true difference of the population proportions. Now, what this means in maybe less technical terms is that the first system does between about 6 and 26 percentage points better than does the second system. And so that indicates that the first system really is better than the second system. And so our original suspicion was confirmed by this confidence interval.